So the next reaction is the reaction between a carboxylic acid and lithium aluminum hydride. So it says to you here what should happen. Lithium aluminum hydride reduces carboxylic acids to alcohols. So what you have is this product right here. Now, and it's of course a primary alcohol. Now there is a mechanism for this that's a bit long. We may go over it in class, but I'm not asking you to know it for the exam. But it's a bit involved. It involves actually an interaction at between the lithium aluminum hydride and this hydrogen here, and then of course it becomes a good leaving group, so on and so forth. Now you cannot directly convert a carboxylic acid into an aldehyde. So you can't go from here to the carboxylic acid. So this is a carboxylic acid to an aldehyde. But you have two alternatives. You can reduce all the way down to the alcohol and then oxidize with PCC. I will talk to you about this in class when we meet, because we need to know a few reactions for synthesis problems. PCC is an oxidizing agent. So if you reduce this all the way down to an alcohol, you can use PCC to arrive at an aldehyde. Or in B, but we're only going to learn this in chapter 22, how to convert. So you're going to go from a carboxylic acid to an ester, and then from an ester, you can use dibol H. We've seen this on the last page. And water, and we can arrive at an aldehyde. Now the next reaction, we're going to finish all of these because we don't have that much left for the part one. Lithium aluminum hydride reduces amides to amines. So basically what you can do very simply is replace this double bonded, this carbonyl carbon double bonded to the oxygen with two hydrogens. So it's going to be CH3. I'm going to draw them out right here. And then of course you have the NH2. Or we simply just draw it this way. CH2, NH2. So that's an amine, a primary amine. Now, the next reaction deals with the stereochemistry of carbonyl reduction, follows the same principle we have previously learned. Remember, if you have achiral reagents react to form a new stereocenter, the result will be a racemic mixture. What that means is that, let's say the reaction takes place, and we knew that when we conducted this reaction, a ketone with sodium borohydride, we added an H. So that means this carbon, the carbonyl carbon, will be a stereocenter. So let's draw it. That's the OH. That's the CH3. We added an H. And then, of course, we have the CH2, CH3. Now, since we have a stereocenter, 4 different groups, then this one can have both enantiomers, the R and the S enantiomers. So then it would have to be drawn this way. So let's say we have OH, H, the CH2, CH3, and then of course the CH3. So that's 1, and then its enantiomer, its mirror image, would be the reflection of it, where you can just draw the reflection here, or you can just switch to bonds. But let's just draw the reflection here. It's not going to be easy drawing the CH2, CH3, but we'll do our best. So these are the enantiomers, pair of enantiomers. And we know if we have a pair of enantiomers, we have something called a racemic mixture. So reactions that give you racemic mixtures are not useful reactions. They're not that useful unless, again, it's done for a specific reason. So we do then have a solution to that. And if we go down here, so if we use a chiral reducing agent, we get what we call an enantioselective formation. Enantioselective means it's going to give you one enantiomer. One enantiomer. The majority will be, almost 99% will be a product that is one enantiomer. Either, let's say, this one, 99%, and 1% of that, or even more. So an enantioselective formation of a single enantiomer can occur. The CBS reagent named for Corey, Bakshi, and Shibata is one example. So we just call it the CBS reagent. CBS reagent. We have the S, we have the R. So if we have this ketone, acetophenone, and we react it with the S-CBS reagent, we will produce one enantiomer. Let's say this enantiomer. And if we use the R CBS reagent, then we will produce the other enantiomer, where now they're switched. So you have the OH now coming out towards you. And the H is moving away. Now, what should be emphasized is that the S-CBS reagent doesn't necessarily get you the S enantiomer, or the R-CBS reagent gives you the R enantiomer. So you should not think of it like that. What you can do is if you use them separately, then you can ensure that one of them will get you the S and the other one will get you the R. There are just many, many factors going in here, depending on what substance you're using. And of course, the size of these groups. So again, but this ensures that you get 99% of a pure enantiomer for the product.